All right, so in this lecture, we will apply the general energy balance to derive the energy balance for a PFR. So to do that, first let's draw the system. So the PFR, we know, is a tubular reactor. And when we have a non-isothermal CSTR, a lot of times we're thinking about like a shell and tube type systems. So something like this. Again, we're going to say the system is actually going to be a volume slice within the reactor. And we say that because the temperature and the concentration of the reactor contents as they progress down the length or volume of the reactor is changing. So we want to pick a system where the contents are well mixed. So we say we can pick any infinitesimally small volume slice along the length of the reactor, and we can consider that to be well mixed. I'm giving this some width here, so this is not infinitesimally small as I've drawn it, but in reality we would take the limit of this slice as the volume goes to 0. So we mark the location of this slice along the reactor, saying it starts at V and it ends at V plus delta V. Coming into the reactor, we have flow rate. Now we're interested in energy, so we are also going to consider that we have enthalpy or heat of formation for each species coming in. And we're also going to be at some temperature coming in, and then coming out, we're going to have all of the same things, but they're all going to be now evaluated at the outlet condition. So coming in at the entrance, I have my reactant species, or maybe some inerts. Coming out, I have unspent reactants and products. But then I also have flow in my shell part. So for example, I could have coolant coming in and coming out. And the coolant, of course, is not reacting. It's not inside the reactor, it's in the tube. Its job is to exchange heat with the contents inside the reactor. So this is we're going to use this system to derive our energy balance. So what we want to do is come up with a set of design equations, just like we did in the isothermal case. When we had the isothermal case, the design equations constituted a mole balance, and if there was pressure drop, then the ergon equation. If we have a non-isothermal system, then we're going to have a mole balance, an energy balance. If there's pressure drop, we'll have an ergon equation. And if the temperature of the cooling fluid is not constant, then we'll additionally have to write a balance on the cooling fluid. So if we can write the mole balance in terms of x, then we would have two balances. The two balances form two equations that would allow us to solve for two unknowns, x and t. If the pressure is also unknown due to pressure drop, then we would add an additional equation, which would be the ergon equation. If the temperature of the cooling fluid varies along the reactor, then we would have another energy balance, but this one would be for the cooling fluid. And of course, if the problem cannot be solved in terms of x, if the mole balance can't be solved in terms of x, then we would need to write mole balances for each species in the system. Okay, so let's derive the balance for the system pictured above. And to do this, we're going to take the general form of the energy balance that we arrived at in the last lecture, and we're going to apply it to that system. So the first thing to do is to cancel terms. So I'm going to cancel the WS term. So in this tubular reactor, there's no moving parts, so that means that there's no shaft work, so that term goes to 0. So now, if we apply the general balance to the system and omit the WS term, we get 0 is equal to Q dot. So we have the heat term from this is the exchange of heat with the heat exchanger, and then we have the flows coming in and out. The Fi are molar flow rates. These are the same molar flow rates from the mole balance. So when we're solving a mole balance, that's giving us the values of F that come into, or that play into this energy balance equation. Q is the heat transfer term. It looks something like this. UA delta T, where this is the temperature of the coolant, and this is the temperature of the reactor fluid. So basically, the heat transfer term is going to give an overall heat transfer coefficient times an area times a temperature difference. So the ordering inside this parentheses is intentional. So if TA is greater than T, then heat is transferred from shell to tube. And alternatively, if T is greater than TA, then heat is transferred from tube to shell. So the nice thing about this heat transfer term, we don't have to make a decision about what is going on. It's already embedded in the way that we wrote our Q term. That means at some points in the reactor, we might have heat transferring one way, and in other points in the reactor, we might have heat transferring the other way, and that's all determined by which fluid has the greater temperature. UA is the overall heat transfer coefficient times the area. So U has units of energy. When I say energy, something like kilojoules or kilocalories per area, per temperature, per time. So we multiply that by an area, and we get energy per temperature per time. When we derive balances for this class, because of the way we write our system, we always have heat transferring over an area, but where we want the heat transfer as a function of volume, because that's going to help us with our balance, we hence introduce a different way to express area. We use this, at least when we use tubular reactors, we use this lowercase a, where a has units of surface area per volume. In that case, we can write our heat transfer coefficient, or our heat transfer term, as a function of volume, which gives the appropriate units for the energy balance. So if we do that, then our balance looks like, so we have this UA delta T times delta V. So what we're doing here, U has units of energy per area per temperature per time. A has units of area per volume, so that puts this term in energy per volume per temperature per time. We multiply by the volume over which the heat is transferring. That means we're in energy per temperature per time. This term, multiplying by this term, means that we're in energy per time, and that is what we need to be in, the units that we need to be in for the energy balance. So if you go back to the general form of the balance, the accumulation is a DEDT term, which has units of energy per time. So all the terms in the balance need to have those units. So by making these manipulations, that allows us to have the units that are required for our energy balance. Okay, so continuing on. We have our flows coming into the system times their heats of formation. So those are evaluated at V minus the flows coming out. times their heats of formation, meaning that those will be evaluated at V plus delta V. So when we do this, we can now apply the definition of the derivative. When we do that, we're going to divide all terms by delta V and take the limit of delta V as it goes to 0. I'm not going to write all of that out, but in the same way that we derived mole balances for tubular reactors, what we will arrive at is this expression. So this is our heat transfer term. Our ddV term is still operating on this term here. So we have two components here. We have the molar flow rates and then the heats of formation. So we actually have to apply the product rule on this term. So if we apply the product rule, we would say dV sum Fi Hi equals sum Fi dHi dV plus sum Hi dFi dV. And actually I did that backwards than what I meant to do, so we'll say the second term. So the second term, this should look kind of familiar. What do you notice about this term? So this is the mole balance, dFi dV, for a tubular reactor, or for a PFR, a PBR, and then multiplied by the heat of formation. So mole balance times the heat of formation. In other words, sum of the Hi dFi dV equals Hi Ri. So if we were to write the mole balance for the tubular reactor, it's going to be dFi dV is equal to Ri. So we can substitute or make that substitution. So the first term, that's Fi times dHi dV. Actually, so for this, we need to take the derivative of Hi with respect to V. So recall that H is equal to a standard value of H at a standard temperature plus integral of Cp delta T. So if we were to take the derivative with respect to V, of this expression, this is just a constant, so its derivative with respect to V is equal to 0. So what we would get is, and I should subscript this, I would get Cpi dt dV. So that's what my the first term in that expression is equal to. dHi dV is equal to Cpi dt dV. So this development assumes that the heat capacity is constant with temperature. This is a reasonable assumption to make for liquids and gases, since we are pretty much only dealing with liquids and gases. Our system, so our system is our reaction fluid. That is almost always, if not always, liquids and gases in this class, so that's a reasonable assumption to make. So we can assume that the the heat capacity is constant. That leaves us with the final form of our energy balance. 0 is equal to UA TA minus T minus HIRI minus FI CPI DTdV. So now this term, so we have a sum of heats of formation times Ri, but all the Ri are related by stoichiometry, so we can use the equation of relative rates to relate all of the rates back to that of the limiting reactant. So what that is saying is Ri equals the ratio of stoichiometric coefficients times the rate of A, or whatever the limiting reactant is. So if we take, for example, this reaction where A is going to be the limiting reactant, my stoichiometric coefficients, nu A equals -1, nu B equals minus B over A, nu C equals C over A, and nu D equals D over A. We can substitute this expression into the energy balance. We would get 0 equals UA TA minus T minus sum HI nu I divided by nu A times minus RA minus sum FI CPI DTdV. So the nice thing about this, when we write this expression here, HI times nu I divided by nu IA, this has a particular meaning. This is actually equal to heat of reaction. So when you're deriving an energy balance, you want this heat of reaction term to fall out of there. If it's not falling out, then you probably have done something wrong, so go back and check. Since some of the heat of formation times the stoichiometric coefficient, given that the stoichiometric coefficients for reactants are negative and those for products are positive, this is going to look like a sum of products minus reactants times their stoichiometric coefficients. That's what heat of reaction is. When we take this on a per stoichiometric coefficient of A basis, so sum HI nu I divided by nu A is heat of reaction per mole of A, or per mole of limiting reactant. So we can prove this. So the formula for the heat of reaction is the heats of formation of the products times their stoichiometric coefficients minus the heats of formation of the reactants times their stoichiometric coefficients. For the reaction above, the heat of reaction would be calculated using this equation, which gives us the heat of reaction on a per mole of A basis. So the heat of reaction in this case would have units of energy per mole of A. This is important. It's important for accounting. When we write into the energy balance that we have a heat of reaction times a rate, we want the heat of reaction and the rate to be in terms of the same component. If we don't do that, then we're going to have an accounting error. So it is important to make sure that the heat of reaction is properly normalized and that it's apparent which species it is written in terms of. This is because it's going to get multiplied by Ri. Ri is going to be written in also in terms of some species, and those species need to be the same. So if we substitute this expression in to our energy balance, we get 0 equals we get this expression. All right, so let's do a units check. Every term in this energy balance should have units of energy per volume per time. So let's look at this term. So heat of reaction has units of energy per mole. In this case, that's going to be mole of A. Ra, we know, has units of moles of A. And we know it's A because we've gotten this subscript here per volume per time. So this term, delta H times Ra, has units of energy per volume per time. So what this allows us to do is write the energy balance as a function of volume down the reactor. So this is now our expression. We can now arrange this so that it looks like an ODE. So to do that, we get dt dV equals Ra times delta H reaction in terms of A minus UA TA minus T divided by sum of the Fi times Cp I. So that's our energy balance. Two important terms in this expression. This term here is heat generated. So the heat generated is due to the reaction. So the heat of reaction times the reaction rate gives the heat generated term. So let's say due to reaction. UA delta T is the heat removed. So the heat exchanger is removing heat based on the heat transfer coefficient and the temperature. So this is due to the heat exchanger. So we're going to see these two terms. We're going to see these terms a lot doing energy balances. We're going to think of these terms a lot. A key in reactor design is to make sure that the heat removal term is adequate to deal with the heat generated term. When these two terms cannot be, or when the heat removal term cannot compensate the heat generated, that's when reaction runaway can occur. So two very important terms. Key point here. We have a reaction releasing heat. How are we going to control that? Okay, so what if the reactor is adiabatic? In that case, adiabatic means Q equals 0. So we don't include the UA delta T term. In that case, we have just a heat of reaction term. We do not have our heat removal term. In that case, what we have is the way the heat is being mitigated would be due to the sensible heat changes of the components. So the components are absorbing heat based on their heat capacity. So that would be the way that heat is removed in the adiabatic case. So two cases here. One is if TA is constant. In that case, it's pretty easy. I just supply a value here, and I have just one energy balance. So supply a value. And I'm done now. If TA is not constant, I need to write another balance on the heat exchanger fluid. And we will do that in the next video.